In this video, we're going to talk in greater depth about winding number, and we're going to introduce the concept of chains and cycles, and then use all of this to state and prove one of the most general versions of the Cauchy integral formula. The first thing we'll talk about is how to form a continuous logarithm along a curve. So given a curve, gamma, mapping into the plane minus the origin, we're going to find a continuous logarithm of this curve, and that should be a little surprising because this domain of the plane minus the origin, we cannot define the logarithm on that entire domain. But it turns out that we can define a logarithm along the curve, which just basically keeps track of continuous values of a logarithm. So if I have a curve going through the plane and avoiding the origin, I can pick a value for the logarithm here and then just continue it as I go. And although if I come close to the original point, I'll have a different value for the logarithm, I do still have a continuous notion of taking the logarithm. And the easiest way to define it is just with our line integrals from before. So we'll define these truncations of our curve. So this will just be gamma restricted to the interval a to t, where t is in the interval a to b. And then we'll define just sigma of t to be this line integral of dz over z along this truncated curve. And what we're going to show is that gamma of t will equal gamma of a times the exponential of sigma. And so sigma is basically a continuous change in the logarithm of gamma. And its imaginary part will then give us a continuous change in the angle of this curve. So the imaginary part of sigma is keeping track of the change in angle as we go from A to B. You could incorporate gamma of A into here and get an actual continuous logarithm of the curve so that you'd have x of maybe some particular value of the logarithm of gamma of A plus sigma of t here. Okay, so then the question is, why does this formula give us what we want right here? And we've already seen basically the right argument. So let's fix a t-naught in our interval. And now for z's close to gamma of t-naught, which I'll call z-naught, I can write down this function g of z, which it'll follow the truncation up to t-naught and then follow a line segment from z-naught to t-naught. And the idea is that this will be computing values of sigma when I put in gamma of t in for z, because this will be homotopic to the gamma sub t curve. But the way we have this is a curve going from z naught to z, and so locally we know that we can take the derivative of this and get 1 over z. So this is a local antiderivative of 1 over z. And we've already seen arguments that if you have a local antiderivative of 1 over z, then something like z e to the minus g, you can just show that that's constant by taking its derivative. I won't go through that argument again, but this will be constant, and so it'll match its value when I put in z naught. But then at z naught, I'm just getting sigma of t naught in for g. So if I put in z naught into g, that's sigma of t naught over here. And so this does exactly what we want. So for t is close to t naught, I can put gamma of t into g, and I'll be following a curve from gamma of t naught and then z naught to gamma of t, and then since this tiny piece of the curve will be homotopic to a tiny piece of the curve gamma going from where t goes from t naught to t, then we get that our g matches up with sigma of t. And so at least near t naught we have gamma of t times e to the negative sigma of t is this constant. And so this expression will be continuous and locally constant, and then you can use connectedness of the interval to show that we get the formula that we want. So you could extend this all the way down to t equals a, where we have sigma of a has to be 0 because it's just integrating over a constant curve. And so we get the formula that we want. We have extracted the change in the logarithm here times the starting value. And so this keeps track of angles and the logarithm of curves that avoid the origin. And we already explained this once, but if gamma is a loop, then gamma of b has to equal gamma of a. So in our formula, we'll get e to the sigma of b has to be 1. So then sigma of b has to be in 2 pi I. And so then for loops, we get that this expression, so I've divided by the 2 pi I, this will be an integer. And this is how we define winding number. And here I've translated so that we're not just talking about the origin, but now we'll talk about curves that avoid other points like z naught. So that our notation for winding number will be w of z naught comma gamma. And so the winding number of gamma with respect to z naught will be given by this formula, and it'll be an integer, which is supposed to tell you how many times the curve goes around a point z naught. And so your loop here has to avoid z naught because we don't want any situation where the curve is cutting through z naught, because that leads to some confusion. But other than that, you can define this for any point that is not on the curve. And let me just talk about one minor variation of what we just did. You can take the continuous logarithm of a function along a curve in the following sense. So this says loop. I don't need it to be a loop. Let's just say curve. So given gamma here, a curve, and given an analytic function that's non-vanishing, I'm going to form a continuous logarithm of f of gamma of t. And I could already do that by the previous approach, but it turns out you can also express it as this integral, and this will be useful later, that the continuous logarithm or continuous change in logarithm of f along the curve will be given by this line integral, where again gamma of t is the truncation. And the argument to show it is just very similar, so I won't go through it. But in the end, what we get is that f of gamma of t, so f along this curve, equals e to the g times its starting value. And this will keep track of how the angle of f, or the logarithm of f, changes. So we're mostly concerned about how the angle changes because the real part of this will just be related to a natural log. So the most important thing here is that this imaginary part of g keeps track of the change in angle of f of gamma as you travel along the curve.